How quantization works. There are around 4 billion values within the set of FP32, possible values ranging from -3.41038 to 3.41038. Whereas with INT8, we see only 256 values within the possible values set, ranging from -128 to 128. Due to the latter being a significantly smaller set of values, matrix multiplication can occur much faster. Due to the immense computational cost of deep learning-based models, accurate and efficient algorithms are essential. The process of quantization occurs by first determining the optimal route of projecting the 32-bit floating point values into the INT8 field. To do so, there are multiple algorithms to quantizing a model. We will take a look at two quantization methods, absolute max and affine quantization. Absolute max quantization. To calculate the mapping between the floating point number and its corresponding INT8 number in absolute max quantization, you have to first divide by the absolute maximum value of the tensor and then multiply by the total range of the data type. For example, we will apply the absolute max quantization algorithm to the following vector: 1.6 minus 0.7 minus 3.4, 1.7 minus 2.9, 0.5, 2.3, 6.2. You extract the absolute maximum of it, which is 6.2 in this case. INT8 has a range of -127, 127. So we divide 127 by 6.2 and obtain 20.5 for the scaling factor. Therefore, multiplying the original vector by it gives the functional data vector 33 minus 14 minus 70, 35 minus 59, 10, 47, 127. Due to these numbers being rounded, there will be some precision loss. 5. Affine quantization. To implement the affine quantization algorithm, we will define our range of 32-bit floating point values as A, B. The affine quantization algorithm is as follows. XQ equals round 1/SX plus Z. XQ is the volation INT8 value that corresponds to the 32-bit floating point value X. S is an FP 32 scaling factor and is a positive 32-bit floating point. Z is the 0 point. This will be the INT8 value that corresponds with 0 in the 32-bit floating point field. Round is referring to the rounding of the resulting value to the closest integer. To next establish the min-max of our 32-bit floating point values, we need to take into account any outliers. Overlooking these outliers can lead to them being mapped as either min or max and potentially skewing the accuracy of the Bushel model. To counter this, the model can be feasible in blocks. The weights can be broken up into groups of either 64 or 128. Then these groups are fully self-perceiving to account for outliers and minimize the risk of lowered precision. Types of quantization. Post-training quantization, PTQ. Post-training quantization occurs when quantization is applied to an existing model. This converts the model from a floating point representation to a lower precision fixed point integer without the need for any retraction. This method does not require as much data as quantization-aware training and is much faster. However, because an already existing model is essentially being converted to a smaller sizer, post-training quantization can lead to performance being degraded. An example of when to utilize PTQ would be when you already have a working model and have a desire to increase the speed and efficiency. This is because PTQ takes place after a model is trained. That is, an already existing model, so a large amount of training data is not required for this process. Quantization-aware training, QAT, quantization-aware training incorporates the conversion of weight during the pre-training or fine-tuning of an RMD. This allows for enhanced performance, but it demands a large amount of computational power and requires representative training data. Overall, quantization-aware training will usually produce a model with higher performance, but it is more expensive and will demand far more computing power. An example of when to use CAT would be when you possess an adequate amount of training data and a larger budget. It is also good to remember that this process takes place during the training stage of the model, so it does not make sense to use this method with a model that is already trained. Dynamic quantization versus static quantization techniques. The purpose of these two techniques is how the clipping range, or calibration, as it is often referred, will be selected. During this dynamic quantization, the clipping range is dynamically computed for each activation. Typically, this type of quantization technique will result in a higher accuracy. As its name states, static quantization utilizes a fixed clipping range for all inputs. This form of quantization is used more often as dynamic quantization and can be highly expensive. Risks and limitations. Lower precision. When the weights are converted during quantization, sometimes there is a loss of accuracy within the virtual values with accuracy machine learning models. Model size should be taken into consideration because when quantizing exceptionally large assets with numerous parameters and layers, there is the risk of significant quantization error accumulation. Cost. Machine learning model scale training can be extremely costly, especially with quantization-aware training, QAT. This makes post-training quantization, PTQ, the best choice from a cost-effective standpoint. However, this does limit the model in some aspects, as QAT will typically produce a more accurate model. TorchServe and Llama.cpp, serving large language models in practice. Welcome to this chapter, where we explore two powerful approaches to serving machine learning models, TorchServe and Llama.cpp. Both tools are designed to deploy models efficiently, but they serve very different purposes and environments. Understanding when to use each one can significantly improve the performance and scalability of your AI systems. Section 1. What is TorchServe? TorchServe is an open-source model serving framework developed by Meta AI. It is specifically designed for serving PyTorch models in production environments. TorchServe provides a standardized way to deploy, manage, and scale machine learning models. It supports features like model versioning, batch inference, logging, and monitoring. It is commonly used in enterprise environments where multiple models must be served reliably and at scale. Section 2. What is Llama.cpp? Llama.cpp is a lightweight, high-performance inference engine written in C++. It was originally designed to run large language models efficiently on CPUs without requiring GPUs. It supports falsifying models in GGUF format, allowing large models to run with reduced memory usage while maintaining good performance. Llama.cpp is widely used for local inference, edge deployments, and fast prototyping of AI applications such as chatbots and retrieval augmented generation systems. Llama.cpp supports various hardware targets such as MUSA, CUDA, HIP, CAN, OpenCL, RPC, x86, ARM, Metal, BLAS, BAS, ZDNN, ZenDNN, SQL, and Vulkan. These backends make up the GGML tensor library used by the front-end model-specific Llama.cpp code. Llama.cpp uses such CPU extensions for optimization: Neon, i8mm, SVE, SVE2, SME, and SME2 for RX64, ARM64, VXE2, Vector Enhancement Facility 2, for S390X, AVX, AVX2, AVX512, AVX-VNNI, and AMX for 8664. Apple Silicon is an important target for this project. Llama.cpp supports a lot of features for inference on edge devices, such as ahead-of-time model quantization and on-the-fly KV cache quantization, partial offloading of model layers to system RAM, which allows devices to load models which would be too large to fit solely in GPU RAM, ahead-of-time model quantization. Ahead-of-time quantization refers to the process of reducing the precision of a model's weights before deployment. Instead of using 16-bit or 32-bit floating point numbers, the model is converted into lower precision formats such as 8-bit, 5-bit, or even 4-bit representations. This process is typically performed once prior to inference, and the resulting model is saved in a compact format such as GGUF. The benefits are substantial. Quantized models require significantly less memory and can run much faster, especially on CPUs. This makes it possible to deploy large language models on consumer hardware or low-cost cloud instances. However, quantization introduces a trade-off. Lower precision can slightly reduce model accuracy, although modern techniques minimize this impact. On-the-fly KV cache quantization. During inference, language models store intermediate values known as key value caches, or KV cache. These caches help the model remember previous tokens and avoid recomputing attention states. On-the-fly KV cache contents reduces the precision of these cached values dynamically during runtime. This significantly lowers memory usage, especially for long contexts, where the KV cache can otherwise grow very large. The advantage is that it enables longer conversations or larger prompts without exhausting system memory. The trade-off is a small potential decrease in generation quality, though in practice this is often negligible. Partial offloading of model layers. Another powerful technique is partial offloading. In systems with both GPU and system RAM, not all model layers need to reside in GPU memory. Instead, some layers can be stored in system RAM and transferred to the GPU only when needed. This allows models that exceed the GPU's VRAM capacity to still be executed. For example, a model that requires 12 GB of memory may still run on a GPU with only 6 GB of VRAM by offloading part of the computation to the CPU and system memory. The trade-off here is performance. While this approach enables larger models to run, it introduces latency due to data transfer between CPU and GPU. Speculative decoding. Speculative decoding is a technique designed to accelerate text generation. Instead of generating tokens strictly one at a time, a smaller, faster model is used to predict multiple tokens ahead. These predictions are then verified by a larger, more accurate model. If the predictions are correct, the system can accept multiple tokens at once, significantly speeding up generation. If they are incorrect, the system falls back to the standard generation process. This method can dramatically improve throughput without sacrificing output quality, especially when the smaller model is well aligned with the larger one. Additionally, Llama.cpp supports various features and APIs for front-end communication, such as grammar-based output formatting as JSON, OpenAI-compatible endpoints like v1/chat/completions. Section 3. Pros and cons. Let's start with TorchServe. TorchServe offers strong advantages in production environments. It integrates seamlessly with PyTorch, supports REST APIs out of the box, and allows multiple models to be deployed and managed simultaneously. It also supports GPU acceleration and batch inference, making it ideal for high-throughput systems. However, TorchServe comes with some drawbacks. It can be complex to set up, especially when packaging models into archive files. It is also relatively heavy and may introduce latency, particularly when running on CPUs without optimization. Now, let's look at Llama.cpp. Llama.cpp excels in performance and simplicity. It runs efficiently on CPUs, uses quantization to reduce memory usage, and has minimal dependencies. It is easy to deploy and works well even on consumer hardware. On the downside, Llama.cpp is less flexible than PyTorch-based systems. It does not support training or fine-tuning directly, and model compatibility depends on conversion to GGUF format. It also lacks built-in enterprise features like model versioning or advanced monitoring. Section 4. Usage scenarios. TorchServe is best suited for large-scale production systems. For example, if you are deploying multiple machine learning models behind APIs, need GPU acceleration, or require model lifecycle management, TorchServe is a strong choice. It is often used in cloud environments such as Amazon Web Services, Google Cloud, or Microsoft Azure. In contrast, Llama.cpp is ideal for lightweight applications. It is perfect for local AI assistants, embedded systems, and fast inference pipelines such as retrieval augmented generation. If you are building a chatbot or a personal AI tool that runs on your own machine or a small server, Llama.cpp is often the better choice. Section 5. Installation and setup. Let's begin with TorchServe. To install TorchServe, you first need Python and PyTorch installed. Then you can run pip install TorchServe torch model archiver torch workflow archiver. Next, you prepare your model and package it into a .mar file using the model archiver tool. Once packaged, you can start the server with TorchServe start model store model _ models my _ model.mar. This will expose REST endpoints for inference. Now, let's install Llama.cpp. First, clone the repository and build it. Git clone https://github.com/gigergonov/llama.cpp. cd llama.cpp. Make. Next, download a GGUF model file, such as a false-fighting version of Qwen or Llama, to run inference /main mmodel.ggufp. Hello, how are you? For Python integration, you can install pip install llama.cpp Python and use it directly in your application. Section 6. Running in the cloud. TorchServe is designed for cloud-native environments. It can be deployed using Docker containers and orchestrated with Kubernetes. You can scale replicas, use load balancers, and integrate monitoring tools like Prometheus. In cloud platforms such as Amazon Web Services, TorchServe is often deployed on EC2 instances with GPUs or integrated into managed services. Llama.cpp can also run in the cloud, but its strength lies in simplicity. You can deploy it on a small virtual machine without a GPU, reducing costs significantly. For example, a CPU-based instance with sufficient RAM can serve a positive model efficiently. This makes Llama.cpp an excellent choice for cost-effective deployments. Section 7. Final thoughts. To summarize, TorchServe is a powerful and flexible solution for serving PyTorch models in production, especially when scalability and GPU acceleration are required. Llama.cpp, on the other hand, is optimized for speed, simplicity, and efficiency, particularly on CPUs. Choosing between them depends on your needs. If you are building a scalable enterprise system, TorchServe is likely the better fit. If you want fast, lightweight inference for language models, Llama.cpp is often the superior choice. Understanding these tools allows you to design systems that are both efficient and practical, whether you are working locally or in the cloud.